Hello, my name is Sven Finney, and this is Physics 2 Lab 5, Telemagnetic Braking with Faraday. Okay, the purpose of this lab is to observe the effects of a changing magnetic field on a non-coulombic electric field. The results of this experiment will be taken from a magnet falling inside of a conductive tube made of aluminum foil. The concept states that such field can create an induced current to counteract the original magnetic force. This concept is better known as Faraday's law. We compare the results from the experiment with a Python model. All right, so the three models being used in this experiment is Faraday's law, which is the top one, saying the EMF is equal to the integral of the non-Coulombic electric field times the total length. And it's also this is the derivative of the magnetic flux, which is B times area. Also we have magnetic force, and we also have Ohm's law as well. Alright, so there's some assumptions that there are only two forces being acted on in this experiment, the force from the loop and the force of gravity. There is no drag present for ease of calculations. System is the magnet, and the surrounding is the earth, which is the force of gravity, and the conducting aluminum tube. Okay, so in the experiment, a bar magnet was used where the user would hold the conducting tube vertically and drop the magnet from the top opening of the tub. A stopwatch recorded the time it took the magnet to fall through the loop length of the tube. The drop was repeated 5 times so that an average time could be calculated. So the length that I found was 0.46 meters, and the mass of the magnet was 0.025 kilograms, and the magnet dipole I used from lab 3 for that magnet, which is about 2. And these are my 5 trials and their times. Also, I did the second dipole moment for the second glow script as 4.656, and I found the red current to be clockwise direction, while the blue current would be counterclockwise, because the magnetic flux increased in the negative y direction, resulting in a blue current counteracting that, and therefore that blue current must be counterclockwise. And this is my glow script code based on using these to find those data and plot points that you saw, as well as calculating the magnetic force on the ring and on the magnet, and using their resistivity too. And these are the results from the glow script. The left one is using the dipole moment of 2, the other one's using 4.6. I can see with the 4.6, in the middle, it's very linear. However, in the beginning, and the end of the velocity versus time graphs, there's some quadratics being used with the curve, meaning that the two forces, force loop and force gravity, are not balanced, therefore resulting in that. And then the very left one, the dipole moment of 2, there is still a little bit of curvature between the beginning and the end too. So what if the resistivity of the conductor were reduced as closely as possible to 0, will the dynamics of the falling magnet change? And yes, because it called for a near zero resistance, a near zero resistivity would be much bigger. The current would increase. When current increases, then the dynamic force would then increase. It causes a force that counteracts the bar magnet. And also, what if holes were cut in the tube? How would this affect the ring currents? They would decrease the induced current, decreasing the magnetic force counteracting, making the force of gravity making more of an impact, making the magnet fall faster. So the conclusion. In short, we were able to observe the effects of the magnetic force under Faraday's law. The results were graphed and compared in glow script, where we concluded the magnetic force is balanced with the force of gravity some of the time. However, the beginning and end of the experiment were unbalanced by the quadratics. It was a constant velocity, which means there's no acceleration. For a more precise experiment, accounting for human error regarding stopwatch timing, errors in coding such as grammar, and noting forces besides gravity, i.e. drag, would be a recommendation. Thank you for watching my video. Hope you have a great one.